So in the previous videos we skipped a portion where we are unable to write in the direct IO. So we have seen that MDL address and we need that function get system address for MDL save function. So we are unable to use that function because it is a macro in the WDM header, Windows driver model header. So here I have found a blog post where they have generated the bindings. So you can follow along, but it is going to take so much time. So what we are going to do is we are going to simply copy paste these projects into our project. So you can go to this link, and in the GitHub repository you will find a Windows kernel RS project. So in this you will have these two projects are important for us, kernel build and kernel RS, sorry, kernel sys. So here you can see what they are doing is they are going to link this with the header files. So we will be using the bindgen crate to generate these bindings. So here we are so here we are returning this function, and this will be linked against this CentOS kernel. So here you can see the definitions, function signatures. We have this get system address for MDL save function. So we can just clone this repository and copy these two folders into our folder. So this is my test driver folder, and I have copy pasted this kernel build and kernel sys. So these will look like this. So you don't need to modify any of these things. All you need to do is go to your driver, your test driver project, and go to the cargo.toml, and you need to write this line: Windows kernel sys is equals to path. We need to specify the path. So if these two folders are in your current project directory, you can just simply put this string. If these folders are one directory above, then you can put like this. So this is what they also show here. So we need to put the path here, and then you can go ahead and import these functions. So for now we are using only one function, get system address for MDL save, that is in this CentOS kernel from Windows kernel sys. So you can then go ahead and cargo build. And one more thing, before building we need to install a compiler called Clang. So you can Google search for Clang Windows and go to this LLVM download page. Here go to this release page and search for Windows Win64, and we need to download this and install this one. After installing this, what you need to do is you need to go to let me show you properties and advanced system settings, and here we need to add this path. So program files LLVM bin. So we need to add the path here, then click on OK, and you will be good to go. So after installing that Clang, you need to just run the cargo build and we will be good to go. So okay, it's very easy. You don't need to follow all of these steps. You can directly clone this repository and copy these folders and install the Clang and build the project. So in this video we are going to see the device IO control. So we have seen up to now how to read and write, create close to the device. So these are the predefined IOCTL codes. So these are the predefined codes. We can also define our own custom code using the device control. So device control is like a custom way of communicating. So the value for the device control is 14, and this is the function the user mode application will use to exchange the data. So the first one is the device handle, and the second parameter is the control code. You can specify your own control code. And the third parameter is the input buffer and the input size. So this application can send any messages like hi, hello there, etc. using this buffer. You can also send a null buffer as well. And the next parameters are output buffer and output buffer size. So the driver will write any of the information to these buffers. And the last one is bytes return. The driver will send you the number of bytes return. So we'll be using this function in our user mode application. So let's declare two arrays, input buffer. For now, let's just give these 4 bytes. Okay, so we can copy this. Output buffer, all zeros for now. And let's go and call the function device IO control, and file handle we have opened using the create file function. And the control code, let's call this 0x69, and the buffer input buffer dot length, and also output buffer pointer. So let's bytes return is equals to 0. Okay, U32. Okay, now we are good to go. So we can print out the input buffer. We can directly print out the bytes return. And also print out the array of output buffer, and print them in hexadecimal. Okay, now we are good to go. So we can go ahead and compile this. So our application is ready. So we will be sending the control code 0x69 with the input buffer pointer and the length, and output buffer pointer and length. So now in our driver we need to handle this custom control code. So again we driver object dot major function, so we'll be writing a function called IO device control. So before that, let's see the IO request packet structure. So the MDL address contains the output buffer address. So the system virtual address is present in this MDL address. We need to write to the system virtual address, and the input buffer is located in the associated IRP. So in this system buffer we will retrieve the address. So in that address we will have the input contents. So let's go and write that function. Change this name to IO device control, and we are getting the IO stack location, and also we need to see the IO stack location, the parameters. We will receive the input buffer length and output buffer length. So parameters, and here we need to search for device IO control. Device IO control. So here you can see the first member is the output buffer length. So we will be this value, output buffer length, will be placed here. So and the input buffer length and also the IO control code. So first let's go ahead and read the contents of this input buffer, which is stored in the associated IRP. So okay, here we are reading the IO stack. So let's say this as in output buffer length. So we are reading from the IO stack location, and the parameters is at the 8 bytes offset. So at this 8 byte offset, the first member is output buffer length. So we don't need to modify this one. So copy this, paste here, and change this to input. And then here the input buffer length is 8 offset from the previous value. So you can just add 8. So we have read these input buffer and output buffer length values. Now let's go and read the associated IRP. So from the IRP, the offset is 18 for the associated IRP. So let system buffer is equals to plus 0x18, and this is a union, so you can directly read the 8 bytes. So we have got the system buffer. And what we can do is we can actually print the string at this address. So we are passing 61 hexadecimal, so it will be I think small lower case w, I guess. So let's see anything anyway. We can just say input string, input buffer string %s, and pass the system buffer. Again, make sure that the input array is ending with null byte, otherwise we will be getting blue screen order, because we will be reading infinitely until we get the null byte. So in the tutorial purpose, we are adding null byte for safety. So we will be reading correctly exactly 4 bytes. Okay, now we have printed the input buffer, so we need to write to the output. So output is stored in this MDL address. So plus 8 onwards, plus 8 offset. So let MDL address is equals to, so copy this code and paste here. We need to change the offset. Instead of 18, give 8. So plus 8. And now we need to use the function get system address for MDL safe and pass in the MDL address. So we are using the transmute function to automatically translate this U64 address into the function pointer of MDL structure. Because we did not define the MDL structure, so we are automatically forcing this one as a pointer to the MDL structure, and the priority can be 0. So that is the normal page priority, and the return value is system VA. So let's call this a system virtual address. So this is the address where we want to write the contents. So if system VA is null, if system VA is not null, then we can go ahead and write contents. So for I in 0 dot dot output buffer length, so output buffer length is given by the user mode application, and we have read into this variable. So the output buffer length will also be the 4 in our case. System VA as U size plus I as U size U8. Now we are going to write the byte 65 in hexadecimal. So I think we are good to go, and then we are updating the status as a success and completing the request. So let's go and build the driver. We got some errors. N bytes. Okay, we remove that N bytes, right? Okay, we can make this as 0. So we have updated this as output buffer length. So I have just tested this code before recording this video. Let's also compare our user mode application. And put a breakpoint at our driver IO device control. So that is the function we have written. So let's continue, and now also run the debug view. Okay, we have hit the breakpoint. So RDX is the second parameter, which is the IRP, IO request packet. So in this associated IRP, you will have the system buffer. So you can just read these bytes 616161. We are passing as an input, and let's also put a breakpoint after the call to the getting IO stack location. Let's continue. So now that function get current IRP stack location gets executed, and in the RAX you will have the IO stack location pointer. IO stack location RAX. So the major function value is E. So which is 13 in decimal. Okay, 14. Sorry, my bad. E. So 14E. And in the parameters, and parse these values as the structure device IO control. So you can see the IO control code 69 and input buffer length 4 and output buffer length 4. And we can go and hit continue. So you can see the input buffer is A, and the output buffer is 656565. So we are writing 4 times the output buffer length. So we have successfully written our bytes to this output buffer address, and the bytes return value is 4. So that's all for this video. In this video we have seen how to send the custom control code to the driver, and the driver will handle according to the control code, IOCTL code. So some of the applications, some of the drivers will completely remove these write and read. So what they do is they do not register their functions for read and write, and they will only have one function registered, that is for device control. So these drivers will check these major function code we have just seen. So we have seen the E value in the major function. So based upon not this one, IOCTL code. So based upon this E also, because this is the device IO control, and then they will check for the IOCTL code. So it is in the IO stack location. So these drivers will check only this code, and based upon that it will do some custom operation like read or write as the driver desires. Okay, so that's all for this video. We also covered this get system address for MDL save function as well. So now you can go ahead and do the write operation we have missed using the direct IO method.